In the last chapter of our probability unit, we're going to explore two different probability models that will allow us to easily find specific types of probabilities of discrete random variables, and as well as find expected values and standard deviations for both. Now, one of these will be one that can probably be done without use of the model, but it is nice to have it available. And it's certainly, once we incorporate the graphing calculator functions for both of these models, which we'll do in a later time, not in this lecture, it'll make life very easy. But first we want to get the basics down, and the first thing is some new vocab, and it's really not dramatically different. It's really kind of putting a name to what we've been doing for a lot of these probability problems, and that is what we have been doing have been called what are called Bernoulli trials. And basically, when we're talking about Bernoulli trials, we're talking any trials that meet the following conditions. There are two possible outcomes: success or failure. Now, you want to be careful about this is the terminology that the book uses: success and failure. But it's more we get what we're looking for, success, and or we don't, which is the failure. Uh, Sometimes people get hung up on the positive and negative thoughts of success and failure. So sometimes we are looking for the number of surgeries that are not successful. That is what we are looking for. So that would be the success, and it's kind of warped sometimes. But there are two possible outcomes: success and failure. The probability of success remains constant. It does not change. When we go back to, we're going to use an example we used way at the beginning of when we were doing the simulations. We're getting sports athletic cards from the cereal boxes, and we had three different cards that we could get, and what's the likelihood in this and that. We're going to return back to that idea, but the probability of success for finding each card remains the same, and the trials are independent. Now, that idea of independence kind of gets a little tricky when we're talking about cases where replacement is not, we're not replacing anything. We're done without replacement, because that means whether we're talking about a card type of problem, or when we're talking about the buying a box of cereal, really, since we're buying a box of cereal that has one of those playing cards in it, doesn't that change the likelihood that we're going to find whatever cards in the box later on? Technically, yes. But what we have is this condition that's going to kind of keep coming back to us throughout the rest of the course. And it's called the 10% condition. And basically it's saying if the sample size is less than 10% of the population, or it is reasonably assumed to be less than 10% of the population, it's okay to proceed with Bernoulli trials, not tries, trials, despite not meeting the independent condition. Well, basically what they're saying is, if the sample size is small enough, it's okay that we're not replacing, and it's technically changing the likelihood that it happens again, because it is changing it, but not enough to say so. That's really what the 10% condition is saying. Right, so we always want to make sure, we always want to be aware of that condition, that our sample size isn't so big. So here's the example from before, before, well, being way in the past. You get famous athletes on cards, trading cards in the boxes of cereals. So we've got 20% contain a picture of Tiger Woods, 30% contain a picture of David Beckham, and the rest are Serena Williams. The rest is 50%. So the types of questions that we're going to be answering are going to look like this. Whoa, wrong way, Avery. So what's the probability that you get a Tiger Woods card on the 5th box purchased? Well, based on what we already know, we've kind of already answered these types of questions. We know that the probability of getting a Tiger Woods card is 20%. And we know that the complement of that is not getting Tiger Woods is 80%. So really what we're looking for here, and this is how we're doing this, is we're saying what's the probability that our Tiger Woods card occurs on trial number 5. And that'll make more sense in subsequent slides. But what we would do is, based on what we already know about probability, is we would do this, right? We'd say, not a Tiger Woods card, not a Tiger Woods card, not a Tiger Woods card, not a Tiger Woods, and then finally get a Tiger Woods card. We'd multiply them together because that's an and statement, the probability of not getting it and not getting it again and so on and so forth, right? We could phrase it as an and statement, and when it's an and statement, it's the multiplication rule. And again, this is a situation where we're really employing that that independent rule, the 10% rule, because technically once we didn't get it, it would change all the subsequent ones later on, but not by enough to say so. All right, so we have about an 8% chance that we get our first Tiger Woods card on the 5th box purchased. Okay? Well, that's an example of the geometric model, and this is all we're going to talk about in this lecture. We're going to introduce the other model later on. But this model allows us to find the probability that the first success will occur on or by a particular trial. And if we define it by one parameter, which is parameter P, which is the probability of success. And how we denote it would be, we're using, just like before when we were using the normal model and we had the capital N, and then in parentheses we had the mean and the standard deviation. Here we have geom and the probability of success. Right? And it's just some vocab here. P is the probability of success. Q is the complement of P, 1 minus P. It's the probability of failure. Now, it's important to note that in this textbook, our textbook uses P and Q. Anything from your formula sheet is going to use P and 1 minus P in all these formulas. So it's important to recognize that it's important for you to know what Q is, and it's the complement of P, which might get expressed as 1 minus P. And X, just like we had before with discrete random variables, is the number of trials until the first success occurs. Right? So our model looks like this, right? The probability that the first success occurs on trial number whatever is the probability of failure raised to the x minus 1, which is just what we did before, right? We said, what's the probability that we were going to find the first Tiger Woods card on the 5th try? Well, we took 0.8 to the 4th, right? Because there were 4 trials and that didn't happen, and it happened on the 5th, right here. P is that last trial when we get our success. So this is one that we probably don't need. We just demonstrated that we probably don't need to use this model. We certainly don't need to bust out the calculator, which we will go over how to do later on in class. It's easier to do in person. But for this particular type of question, but it's not hard to get to a place where, yeah, it probably is easier to do it with the calculator, right? But that's it right there. We take our probability of failure and we fill it up with all but one of them because we're looking for the first success. And then it's essentially the multiplication rule. Right? So if we were to look at this and make it slightly different, right? What's the probability that the first Tiger card is found in one of the first 3 boxes purchased? Okay? We're still using the geomet model 0.2 because that's the probability of success, right? And we're going to look at it. So really what we're doing is we're still using this, but except we're now looking to expand it out a little bit because what we're looking for is we're looking for the probability that X occurs by the 3rd trial. So it's less than or equal to 3. So we're looking for the probability that X is equal to 1 plus, because it's either the 1st or the 2nd or the 3rd trial. So that's what we're really doing right there over and over. You know, we're setting up 3 different versions of this right here. And with the actual numbers involved, we would say The probability that it happens on the first try, well, that's easy. It's just 0.2. We get it on the first try. The probability that it happens on the second trial, well, we don't get it on the first and we get it on the second. And then we keep going as far as we need to go. And that's the work being shown. We're going to find a way if we get the calculator to spit this number out so we don't have to actually do this calculation. Probably wouldn't be that hard to do, even if we had to, though. Right? So the probability that within 3 is pretty straightforward. We're going to talk about in class, we're going to talk about some other ways that we can kind of be, once we turn this inequality symbol around, we're going to be using the complement of this idea, but we'll talk about that more in person. Okay, so that's one way we can use the geometric model, is to say by the first trial or by whatever trial, and we just have to kind of do however many for now, or this is what we always have to show, but how we get this number is going to change. Right? And then lastly, you could get the question that how many boxes would we expect to purchase before finding a Tiger card? Again, same model with the same parameter, except now we're going to look at it, and that word right there, expect, that should be kind of fresh in our minds, because that's just what we were doing in chapter 16, was finding expected values, which was the mean of the discrete random variable. It's still the mean here. It's the average of what it would be. So if we have an expected value, we also have a standard deviation. Now we could get to the math. I'm sure, I think in the book, they have these things called math boxes where they actually derive all these formulas. There's nothing really that is all that important for you to see, I don't think, to see the derivation of it. But if you wanted to find the expected value, like by what trial would we expect, we take the probability, we 1 and divide that by the probability of success. Right? So in our case here, how many boxes would we expect to purchase before finding a Tiger card? Well, okay, here it is. Shouldn't be that hard to wrap our heads around and say, oh, 20%. Oh, okay, so 5, right? We would expect by the 5th to have found the first Tiger card. Does it mean that we might go that we could we couldn't find it on the 7th? No, that doesn't mean at all. But this is what we would expect. We expect to find it by the 5th. If we find it on the 7th, we're probably not concerned. If we find it on the 22nd, however, well, then maybe something's wrong with one of these numbers. Maybe these numbers aren't exactly what they say they're going to be. And again, that's where we're headed toward with the inferential statistics. Right? And then anytime we have a mean, we should have a standard deviation. And it's this gnarly looking thing here, where it's the square root of q divided by p squared. Again, it's really not that important to see where it all kind of comes from. But if we ever have to employ the normal model, because sometimes these trial numbers get really big, and it's easier to just work with a z-score. You want to have a mean, you want to have a standard deviation. Okay, so that's the geometric model of the first of 2 probability models we're going to be covering in chapter 17. I'm going to have you try some practice work now, and then in class we're going to maybe discuss, in smaller groups, some of the fine-tuning of these problems and how else they might present, and how else the geometric model might present itself. We will also definitely incorporate the graphing calculator as well. Right? So please give the problems that follow this lecture a try, and please let me know if you have any questions. I hope this helped.